Our next speaker is Dr. Barry Wilkins. Barry is recently retired as a senior paediatric intensivist at the Children's Hospital of Westmead. He received his early training in England and before moving to Australia 28 years ago, and has been a paediatric intensivist at Westmead, the Children's Hospital of Westmead, since then, with an interest in physiology that's dated from his university days. Thanks, Barry.
All right, so thank you for coming, guys. Back to the future, I've called this, which is what I really mean is if we're going to look to the future, we need to look back. So we can first look back to the middle of the 18th century. Now, when I was in Boston in 2004, I made a point of going down to the old City Hall. Just inside the entrance, there is this plaque which commemorates the fact that it was originally built as a public school, and in the middle of the 17th century. And this cartouche here shows some children playing in the playground in the middle of the 18th century. This guy became a famous architect. This guy became a famous orator. One of these other guys was the guy who rode his horse to announce the arrival of the British fleet during the American War of Independence. But this boy over here is flying his kite. So that identifies him as Benjamin Franklin. And Benjamin Franklin, as you know, is one of the most intelligent men ever to have existed. He knew about hydrogen becoming a proton, which is all about acid. The one thing he did get wrong, about the only thing he ever got wrong, was that he said that electricity went from plus to minus, and we know that electrons flow in the other direction. But I think we can forgive him for that. Now, there's a whole list in the 19th century of famous people. There's Henry here, there's Faraday, who invented these terms. The word anion, for example, is from Greek, meaning go up, and cation goes down, and things like that. Le Chatelier, a very, very important person who applied the law of mass action to equilibrium situations in physiological fluids. I just gave you a photograph of Arrhenius here just to show that these people really were, human beings. And notice that by the end of the 19th century, we knew all about ions, we knew about dissociation of acids, we knew about dissociation constants, and they had been measured, for example, by Ostwald. And then at the beginning of the 20th century, here is the greatest hero of all, Lawrence Joseph Henderson, a Harvard man, medically trained but didn't practice medicine much because he devoted his life to physiology and biochemistry. And it was he who discovered the buffering power of what he called carbonic acid, carbon dioxide dissolved in water. And he is reputed to have invented this equation. We'll clarify that in a little bit. He also wrote a book based on a series of lectures. I've got a copy of this book. It's very, very difficult to get hold of, which is called An Inquiry into the Biological Significance of the Properties of Matter. And in this book, he argues that the entire biomass, that's the totality of all living forms on Earth, is essentially manufactured out of carbon dioxide and water. And therefore, isn't it sensible, he said, that carbonic acid and its base bicarbonate form the basis for buffering metabolic acid. Now, here he is again. So he applied the law of mass action to carbon dioxide. Another guy, as is him over here, he was a failed medical student who failed to qualify and went to work in the Carlsberg Brewery laboratory and spent his life there. In fact, it's not quite as silly as that, because that laboratory has done a great service to medical science over the last 100 years. And he logarithmized the hydrogen ion concentration. That's how he wrote pH originally. So that's Sørensen. I'm not sure I pronounced that quite right. Hasselbalch was another, he was a Dane, and Hasselbalch was another Dane. He invented some other terms. William Mansfield Clarke came along and changed the nomenclature of pH, and it was he who first invented the term buffer. Who's that over there? That's Donald van Slyke. He's another hero, an American who worked with William Clarke. He published hundreds of papers. He was medically qualified, but he was a biochemist. And in 1917, he wrote a seminal paper demonstrating that in patients recovering from serious illness in which they were acidemic, the acid load could simply be defined by half the body weight multiplied by the change in the bicarbonate. A very simple equation, which we can show still applies today. A few years later, he started experimenting with whole blood in a bottle taken out of subjects in a bottle, and it can be argued that medical educators concentrated on that rather than his earlier work, which was much more simple. And when we come to the Danish school later, we'll see how that eventuated. He then invented an apparatus. It's called the Van Slyke Apparatus to measure bicarbonate in blood. This apparatus is still used to this day in laboratories to measure total carbon dioxide or bicarbonate in blood. When you send your sample to a laboratory, not into the blood gas machine, that's what will happen. They will use a Van Slyke apparatus in some laboratories, a modern version of it, of course. He titrated albumin, first horse albumin, and then human albumin. So we already knew the buffer curve of albumin 90 years ago and more. Singer and Hastings were also American. They invented the term buffer base. Notice this is all now in the first half of the 20th century. So going back, we see that a foundation was laid for our understanding of carbon dioxide and bicarbonate and other buffers in physiological situations. Then the Danish school came along in the 1950s. Astrup here, he was an anaesthetist. Severinghaus was a respiratory physician. And this is Ole Sigurd Andersen. He is still alive in his late 80s. And they made a huge contribution to the understanding of blood gases, starting with the polio epidemic in Copenhagen in the early 1950s, which resulted in the beginning of intensive care medicine, as you well know. It was Ole Sigurd Andersen who invented the term base excess, a term with which you're very familiar, but which we can argue is a little bit suspect. And he developed Van Slyke's nomograms for acid base. They weren't new, but he developed them a little bit. So that's some of the history of acid base. But one other person came along, and that was a very famous man, James Gamble. He was a pediatrician, but he was also a physiologist, and we can attribute the ionograms that we're familiar with to him, which are also called Gamblegrams in his honour. I'm going to come back to those in a moment. The term anion gap was invented very late, but only the term, the concept, was already well known. And in the 1980s, people started talking about, and this is in my time, quantitative acid-base chemistry. But I need to tell you, the word quantitative was used by Donald van Slyke how much earlier? 50 years earlier, 60 years earlier. So it's not a new term. Quantitative acid-base chemistry was already worked out by the famous Lawrence Joseph Henderson, Donald van Slyke, and this man, James Gamble. So we're going to do. So we've had a bit of a. And his son wrote an article called "A Wrong Turn in Acid Base." I'm going to come to that right at the very end. Now let's have a chemistry lesson. Here's carbon dioxide in water. the reputed molecule H2CO3, carbonic acid, does not exist, chemists tell us. So this is basically the dissociation of carbon dioxide and water into hydrogen ions and bicarbonate, which is the basis of acid-base chemistry in physiological situations. It has a dissociation constant. Now, we know that it is now 10 to the minus 6.1. Lawrence Henderson knew that, but what he knew is something that modern acid-base theorists seem to have forgotten, which is that the dissociation of carbonic acid into bicarbonate has also got to be measured against the dissociation of sodium bicarbonate, which also has its own dissociation constant. So this dissociation constant is a composite, which we now know is true in physiological fluids at body temperature. And that is the equation which has been labelled, that's a different version of it, the Henderson equation. Now, Henderson never wrote that equation down, so it's not true that this is Henderson's equation. Henderson just wrote it very much more simply, like that, for any acid. Now, he was looking at phosphates as well as the carbon dioxide system. And that was many, many years earlier, at the beginning of the 20th century. And remember, Hasselbalch came along and logarithmized it, which made a problem for all of us ever since. As you well know, the HendersonHasselbalch equation really just does not exist, at least it should not be called that. Now, here is a curve. I want you to look at the bright green curve. The blue box is the limit of survivability, okay, from a pH of less than 6.6 to over 7.8, and the bright green curve is the buffer curve. Now, at a physiological concentration of about 1.5, only half a millimole of acid can be added before the pH has dropped. So we can exclude phosphate in extracellular fluid as any possible buffer. Here is the same for albumin. The straight line, by the way, is a modern attempt to turn it into a straight line from a curved line, but the bright blue line is the buffer curve for albumin. It's a very generous concentration here of 45 grams per litre. And notice we can only buffer 4 milliequivalents per litre of acid before we are in, dead territory because the pH has dropped too much. And now I've put those two on top of each other. Here's the bright green curve for phosphate. Notice it's irrelevant, albumin is small, and the red line is the buffer curve for bicarbonate. So remember, Lawrence Henderson said that bicarbonate is the buffer in physiological fluids. And the orange line is what happens if you drop your PCO2. You can buffer even more, and you can buffer up to 24 millimoles per litre of acid using bicarbonate when you can only do 4 for albumin. So any attempt to try and persuade us that albumin and phosphate are hugely relevant in buffering acid really is not going to work. Bicarbonate is the buffer, and it is ideally suited to that. I mentioned James Gamble and his Gamblegram. You've got to add up all the positives, and they have to add up to all the negatives. Although there's quite a lot of negative charge on albumin, we have noted that that cannot soak up hydrogen ions very much. It's the bicarbonate species which is the buffer in plasma. Right at the bottom right there, I've shown you a little tiny box which is called the strong ion gap. That really is everything that's left over on the negative side after you've measured everything else. It can only be calculated. To calculate it, you've got to measure sodium and potassium and all these others, chloride. The bicarbonate gets calculated in the blood gas machine. You can calculate the negative charge on albumin if you really want to do it, and on phosphate. But do you really think that all of those can be measured so accurately and precisely that you can actually measure properly this thing that's called strong ion gap? I really think probably we can't actually do that. Now, there are 4 determinants of pH, And I've circled them there. The carbon dioxide, the total amount of albumin, the total amount of phosphate, and the total amount of negative charge on the buffers. But you cannot measure the total amount of negative charge on the buffers unless you measure the pH, the hydrogen ion concentration. But look, what is the physiology doing? How does the body regulate the hydrogen ion concentration? It does it by a fast method by regulating CO2 and a slow method by regulating bicarbonate. And that's how it's done. It is as simple as that, and that was worked out right at the beginning of the last century. Just tell you about the great transatlantic acid-base debate. Now you'll know when you have a blood gas printer in your hand, and on it you've got something called the base excess and something called the bicarbonate. They've both been calculated by the blood gas machine. The base excess is calculated by a complicated equation which Ole Sigurd Andersen worked out. But the Boston School, remember Henderson came from the Boston School, but in the 1960s and 70s they argued that the Danish school were playing with blood in a bottle and it had nothing to do with real physiology. So Denmark gave in. Ole Sigurd Andersen suggested that we should perhaps exclude the hemoglobin component of base excess. Now I want to emphasize that happened 50 years ago exactly. Okay? It's half a century since Ole Sigurd Andersen gave in. There's huge problems you see with base excess. It's based on blood in vitro. It came from healthy adult volunteers. The blood gas machine assumes that the patient's got a normal albumin and phosphate and sodium concentration. And the buffering of hemoglobin is very complicated and influenced by PCO2 quite heavily. So have a look at this. This could come from any set of patients because these points are calculated from only pH, PCO2 and hemoglobin. On the vertical axis you've got base excess, on the horizontal axis bicarbonate. And notice quite a lot of scatter. This is all because it relies on a quantity called base excess which is derived from experiments on blood in vitro. Let's put that aside and do what Ole Sigurd Andersen agreed to do and remove the hemoglobin component. Do you notice the straight line is what would happen if the base excess was identical to the bicarbonate? And you'll notice that nearly every patient, it is pretty well identical. If you put those on top of each other and then look at the plasma base excess, we find that they are so close. And this group of patients down the bottom left here are nearly all patients with diabetic ketoacidosis. So Lawrence Joseph Henderson was right. Okay, he was right in proposing that the carbonic acid bicarbonate buffering system is the buffering system. I mentioned that James Gamble's son, James Lauder Gamble Jr., wrote an editorial in the American Journal of Medicine, I think it was 1986, in which he was called, in retrospect, a wrong turn in acid-base physiology. The wrong turn, he said, was base excess, because bicarbonate had been shown 100 years earlier, oh, not quite 100, 80 years earlier, to be the real measure of metabolic acidosis. And even 50 years after Ole Sigurd Andersen agreed that that was the case, we are still paying attention to base excess. So, ladies and gentlemen, chair entities, fellow scientists, can I propose that if anyone tries to persuade you that there is a new theory of acid-base, please put it aside. There can be no new theory. It was all worked out 100 years ago, and we do not need anything new. I wish I had time to tell you finally about the great 21st century lactate hoax. Do I have time? 1 minute?
You have 1 minute.
1 minute? Okay, let me tell you about the great 21st century lactate hoax. I actually heard this said. Lactic acidosis is actually lactic alkalosis. What a load of bunkum, okay? In fact, they said, look, I've heard this said in a lecture by an extremely eminent person. Look, a proton is actually consumed in making lactate. Therefore, surely it's a lactate alkalosis. Here's pyruvate, which is one of the end products of glycolysis. And here is the proton getting consumed in the production of lactate. Now, have a closer look at that equation. NADH and the NAD plus is a system of doing oxidation reduction reactions inside the cell. So why is lactate being produced? Now look at the formula for pyruvate, C3H3O3, lactate C3H5O3, both with a single negative charge. What has happened is that lactate has taken up two hydrogen atoms, okay, and the hydrogen ion is involved in converting NADH into its oxidized form. So why is lactic acid being actually produced in emergency situations? It is simply because there is a crisis going on where NAD plus molecules need to be produced to help the cell get over the crisis. So lactate has acquired two hydrogen atoms. NADH, that's nicotine adenine dinucleotide reduced form, has been oxidized and has acquired the positive charge. So this is the formula for glycolysis if lactic acid is the end product. Glucose gets split in half, the carbon atoms are rearranged, and lactic acid is produced. And we know that cell membrane monocarboxylic acid transporters that transport negatively charged monocarboxylic acids like lactate also eject a proton as they eject the monocarboxylic acid negatively charged ion. So when you see lactate in blood, which we know is associated with mortality very powerfully, it is because lactic acid has been ejected from cells in crisis situations. So please, lactic acidosis is lactic acidosis. Okay? And that's it.
Thanks very much, Barry. We haven't any time for questions now, but Barry, I'm sure, will be happy to answer questions at the end of the session.